Okay, Rodrigo, so you are good to go. We are so far perfectly on time. So, as I mentioned in my intro, you come from the construct. The construct plays a key role in both education in the ROS toward as well as R&D and consulting. So, as I share your screen, introduce yourself to our audience, and best of luck with your presentation.
Thank you. Thank you. Yes, I will make this slide presentation. Okay, so hello everyone. My name is Rodrigo Gonzalez. I am the head of robotics at the Construct. And a little background on myself. I am from Mexico. I live in Barcelona. And I studied mechanical engineering at Boston University, and I have a robotics master's degree from the UPC, Barcelona Polytechnic University. I want to thank you, Angelo Corsado, and Julian Enoch, and Daniela Anastase for inviting me to speak at Zenoh's yearly user meeting, as well as for the excellent support that you guys always provide through both Zenoh's Discord server and also direct communications overall. So today I'm going to talk about our journey with Zenoh at the Construct. More specifically, how we use Zenoh in our products in order to ensure fast and lightweight connectivity for all our robots. So what do we do at the Construct? We are the largest online robotics academy in the world, and we provide tools and resources for learning and developing robotic skills and programming. We also offer online and in-person intensive trainings for autonomous navigation, manipulation, fleet management, etc. And as the head of robotics in the Construct, I am in charge of developing and maintaining cloud-enabled solutions for our students to practice and develop their algorithms in real robots. So our students practice in real-life scenarios connected to our remote robot labs, which you can see in this video here in the images, through our platform. And ROS2 is our main focus, as with most open source robotics development today. And let me show you a video from our robot cafeteria, which uses Zenoh and is my example today. It's a short 3-minute video. So there you go. That's a basic overview of our Starbucks coffee. We call it the cafeteria. Um, this is enabled by OpenRMF Fleet Management. This is created by Open Robotics. And so as you saw, there's a lot of robots in play here. So coordination between all robots is required and expected. So let me direct your attention to the diagram here on the right, which represents the communication flow between the student, which will be at his or her laptop, to our real robots in our office. So our student connects to our cloud platform, where they develop their projects and launch OpenRMF and basically any other program they want. And then that goes to our real robots in the cafeteria. However, this can be done with a single robot with a default off-the-shelf humble ROS2 humble DDS configuration. However, with more than one robot, especially as you expand, the default DDS implementation, the setup off the shelf with ROS2 humble is impossible. It's just very, very hard to make it to work and have every robot discover each other robot easily and quick and reliably. And Zenoh provides the solution for this problem. So let me talk about the issues we encountered before implementing Zenoh. So issues before Zenoh. I first want to mention the main problem that happens with a default multicast DDS discovery setup. So on the right here, you can see an image of a router traffic monitor or router with a huge spike on the right, a blue spike of traffic that happens when we launch all the nodes that are needed for this system to work. So that's a huge number. That's like 2 gigabytes per second, which of course causes everything to crash down and connections to drop everywhere. And so it's a huge problem. And so we want to be able to limit this. And another issue is that DDS communication can cause problems in limited hardware. So things like CPU usage at 100% can happen if the discovery is too high, like it's trying to discover every single participant in the system. And usually software validation occurs in really nice, powerful robots or simulation. But in this case, it's so issues like extreme CPU usage or things like that on a robot are often hidden beneath the surface. So the combination of these two main problems leads to a slow response, crash prone, and robots that just do not respond as they are expected to. Of course, the higher the number of ROS2 nodes you run, the worse it gets because they need to be discoverable. And we can limit this with a custom DDS XML configuration, but it is not enough. ROS2 manufacturers, ROS2 robot manufacturers might not include this option, which was the case in the beginning for our setup, and can break the chain of information flow. So this was not enough to solve our slow and problem here. So this is the solution, or a diagram of the solution we implemented with Zenoh. So as you can see here, it consists of a main server at the top with the robots connected to that main server. And this is scalable, so that's why you see robot 1, robot 2, robot 3, all the way up to robot N. So the way we did this is running a Zenoh router and a Zenoh DDS plugin in each of these agents, each robot and the main server. And we can specify the endpoint connections for each robot to go to the server, and the main server to listen to all the endpoints to be able to communicate. Another thing that I want to mention that really helped our hardware limitation that I talked about in our previous slide is the ability to separate our robots in different ROS domain IDs. So you can see how the main server has a ROS domain ID of 0, robot 1 of 1, and so on. So this is especially helpful for things like hardware limitations. You can see here that robots are actually attached to a great robot, an iRobot Create 3, which is the base of our robots that bring the coffee around that you saw in the video. And this was the problem of the CPU usage that we had, and being able to separate the ROS domain IDs allows us to isolate that robot in order for the Create 3 to only see what's coming from the robot, which is basically a Raspberry Pi or a simple computer like that. So that way, you're not getting all the information from all the other robots or the main server that might affect the performance of the Create 3, this base, which is basically a black box for us. And so a combination of those two elements is what helped us solve this problem. And again, this is scalable, so you don't have to worry about the amount of robots added to the system. I guess in this scenario, until you run out of ROS domain IDs, but we haven't reached that point, so I guess we'll cross that bridge when we have to. And yes, something that is not pictured here, but is also very helpful, is the topic control flow that you can specify in the Zenoh DDS plugin. For example, the robot might care about the sensor information, for example, the LiDAR information or the odometry information within that subsystem. But in reality, the main server does not care about all that info from the robot. So you can just allow certain topics to go through with Zenoh DDS plugin. And for example, the main server only needs to call action servers running in the robots in order to control them. So maybe the battery level, things like that. So this, what I call the topic control, you decide what can go through and what can't, is also another element from Zenoh that we use that practically solved all problems. So yes, that is basically our solution. Very simple, just running a router and a DDS plugin in all our agents and separating in different domain IDs in order to ensure that no DDS data is sort of leaving the robot and interfering with the communications that might lead to the multicast or problems with the network that might arise. I'm not a networking expert, but this is exactly what I'm looking for a solution, is to just run a couple of things that make the middleware invisible, so I won't have to worry about it. So after this solution, we can take a look at our issues after Zenoh, which are none. The communication flow that we had in the earlier diagram in the challenge we faced is now complete. So the student at their laptop can connect to our platform and then connect to our real robots, all with the help of Zenoh, and there are no issues with communications, no drops of messages, nothing like that. So that is a great solution implemented. And then I want to say a couple of takeaways for this presentation is that in my experience, Zenoh provides the best solution to connect multiple ROS2 robots. I was listening to Angelo talk about, the off-the-shelf, how it works, ROS2, what do you expect to happen versus what actually happens. And of course, there are many ways you can solve this, but I think Zenoh provides the quickest and best solution available. Another thing that I really like is that Zenoh can be used even in the simplest robots. So in this case, a Raspberry Pi, or even smaller. I'm sure a Raspberry Zero, one of those can work with the communication, and it prevents these CPU usage of a smaller hardware limitations that you encounter in the real world, which is what we're looking for. And this extra layer that allows with your DDS plugin that allows control of the domain separation, so you can ensure nothing's going out that you don't need, as well as selecting specific topics you want to bridge over the network can help a lot, especially when you start thinking about things like heavy ROS2 messages in topics like point cloud messages. I know this is a huge problem to wirely transport through the normal default ROS2 setup, and Zenoh solves that really well. And yes, that is basically all I had to say about my presentation. I hope you liked it, and I'm ready to take any questions you might have.
Thank you very much, Rodrigo. That was a very nice presentation.
Thank you.
So, question. Yeah, thank you. I hope you can hear what is here. And many virtual clap from the community, because the bulk of the people are watching online. So question will be posted on social media. So please keep an eye on the chat, and
Okay.
we'll answer a question. We'll answer a question that way. So that said, let me bring on Peter. So let me just do this. So Peter, here we are. Hello, Peter. How are you?
Hello, good.
So great to have you on. So Rodrigo, once again, thank you very much. Great presentation, and I'll now phase you out.
Thank you.
Thank you very much.